Okay, so now let's talk about an application, if you will, of power series. This integral, e to the minus x squared dx, if you think about all the different integral rules, techniques that we have, there's not going to be one of them that's going to help us out one bit on that. U substitution is no good because the power is minus x squared, so we'd have an extra x, if you will, in our du. Parts, there's not enough parts to do parts, right? So anything else? Really all that's left is, you can approximate it, and that's hard to do since it's an indefinite. Yeah, so this infinite series gives us a way to evaluate this integral because of that e to the minus x squared. For one thing, that's related to, very strongly related to a Maclaurin series. On our little formula sheet there, e to the x as a Maclaurin series is x to the n over n factorial, n equals 0 to infinity. This is e to the minus x squared, so basically what I can do is plug in minus x squared there. So I'd get minus x squared to the n over n factorial, n equals 0 to infinity. Now, that is just what I can substitute for here. And let's go ahead and write out a few terms. So if I did n equals 0, I'll have 1 over 1, so that's just 1. N equals 1, I would have negative x to the 2 over 1 factorial, and then n equals 2, I'd have negative, I'd have positive x to the 4th over 2 factorial. If I did n equals 3, I'd have negative x to the 6th over 3 factorial, so I think we can see the pattern there. It's alternating signs and even powers of x. Anyway, here's the deal. So this says this equals that. And if you'll notice, the radius of convergence is it's infinity, so it's good for infinity. But anyway, so if this equals this, I can do the integrals of that, can't I? That's just power rule application there. And so this integral becomes the integral of 1 minus, let's just write it simplified. I'm not going to do the factorials, but everything else I'll. Yeah, so we can see the pattern. And, but we can integrate that because now it's just a sum of sums and differences. And so the integral of that, let's say antiderivative of that is x. Antiderivative of that is minus 1/3 x cubed. 2 factorial, that's just a constant. And so the antiderivative is just the antiderivative of x to the 4th, which is 1/5 x to the 5th. And then that's minus 1 over 3 factorial, and then times the antiderivative of that's 1/7 x to the 7th. On and on we could go. The only other little catch here is this is an infinite, an indefinite integral, and so we do need to add in a constant. Since it's infinite that way, because that just keeps going, the pattern keeps going, and you can see a pattern there. But we do need to add in a constant. So yeah, that's, as an infinite series, that's what that integral evaluates out to be. Just using the Maclaurin series. Now, one other way we could write this, because of the pattern and all that, these are odd powers, and what we could do is kind of write that using our summation notation. Let's see, so maybe better to look at maybe this one. So this would be n equals 0, this would be n equals 1, this would be n equals 2, this would be n equals 3, okay. So focusing on, we got the alternating sign, so I would need that. The first one's positive, so it would be -1 to the n would work, because that would be +1, that would be -1, that would be as far as the alternating sign, so that would work. Then the top is, we got 1. Yeah, like I said, if you look over here, the other thing we've got is, well, we've got 3 factorial. That's n factorial, isn't it? This 1/7, of course, the power and that number there are matching each time, and it would work there. But they're odd, just odd. And so to just get odd numbers from sequential numbers like this, remember that's the 2n plus 1. And I believe that would work because if we do 2n plus 1, that gives me 7. 2n plus 1, that gives me 5. 2n plus 1, that gives me 3. So that's how I get these. Write it in summation notation, just FYI. You don't have to do that, I guess. But that'd be another way to do it, or to write it. And then also, we could note here that if I go back to this, got me history note here, another way I could write this, I could just say, well, it's the integral of that, and let's write that as -1 to the n, x to the 2n over n factorial. Kind of just a power rule here, isn't it? I mean, you've got to add the c in, but bring down the power, add 1 to the power, bring down that power and divide by it. So, same thing. Turns out, so. Anyway. Is that okay? Questions on that? Look all right? All right, well, the problem with what we just did there was we used that Maclaurin series, and yeah, that one had an infinite radius of convergence. Some of them have just a radius of convergence of 1, and they're centered at 0. So sometimes we don't want them centered at 0. So Maclaurin series may not be the best thing to use. Yeah, so we might just want to open it up to Taylor series, and that's kind of where we're going to go next here. Let me talk about Taylor polynomials. And just to sort of review again, remind ourselves here, Taylor series of f centered at A is f of x equals summation n equals 0 to infinity, the nth derivative at A divided by n factorial times x minus a to the n. Well, so that's, that goes to infinity, 0 to infinity. And so we could write out term by term what those are. So the nth 0, so yeah, if we do n equals 0, f parentheses 0, that's just f of a. But we might as well cut to the chase there. 0 factorial is 1, x minus a is 0 is 1, so the first term is just f of a. All right, then we do n equals 1, parentheses, f parentheses, power, looks like power parentheses 1, but that's just the first derivative, so it's f prime at a divided by 1 factorial, but that's 1, times x minus a to the 1. And then n equals 2, we'd have the second derivative at a divided by 2 factorial times x minus a squared. And then third derivative at a 3 factorial. It gets kind of repetitious there, or pattern developing. That's what the Taylor series is. And so yeah, sometimes we do have to write that out, and that's what we're going to do next here with these what are called Taylor polynomials. So by definition, a Taylor polynomial degree n, and it's going to be denoted T sub n of x, T for Taylor. So the degree is n for function f about a, or centered at a. What it is it's just the partial sum up to n. So it's the partial sum of the Taylor series up to n. So for example, T2 of x, that's n equals 2, and so I would just do this Taylor series up to n equals 2. Here's n equals 0, here's n equals 1, n equals 2. So T2x is the partial sum up to that. So T2x is f of a plus f prime of a over 1 factorial times x minus a, 1 factorial 1, plus then second derivative at a divided by 2 factorial times x minus a squared. So just go up to that n, n bound. Call it Taylor polynomial. All right, so let's do one specifically. So let's find T3x for f of x equals cube root of x centered at a equals 1. Well, T3x, I just do the Taylor polynomial up to n equals 3. Do the Taylor series up to n equals 3. All right, so the Taylor series, and so this one, no real need to write it out in summation form, because I want you to write it out term by term here. So the Taylor series, we just start off with f of a, which in this case a is 1, so I do f of 1. Then I would do f prime at 1 divided by 1 factorial times x minus 1 to the 1 plus f second derivative at 1 divided by 2 factorial over x minus 1 squared. And then do it to n equals 3, so I would go to f third derivative at 1 over 3 factorial times x minus 1 cubed. So this, basically what it is, we're just writing out terms instead of using the summation notation. And then evaluating some more here. It's probably a good idea to, when we were doing these Taylor series before, we were doing so many derivatives, fourth derivative up to the fourth derivative, something like that. It's probably a good idea to do the derivatives to the side somewhere. So f of x is the cube root of x, or x to the 1/3. So the first derivative is 1/3 x to the negative 2/3. Two derivatives here. Then the second derivative would be, bring down the power, so it would be negative 2/9 x to the minus 5/3. Third derivative is what we need. So that's 10/27 x to the minus 8/3. And then we're going to evaluate those specifically at 1, which that'll be pretty easy. And so this T3x, all right, so f of 1, we plug in 1 there, would be 1 to the 1/3, that's 1. F prime of 1, all right, so f prime of 1, x is 1, chose the easiest value there is, what's beside 0, I guess. 1 to anything is 1, so f prime of 1 would be 1/3, and 1 factorial is 1, so I don't need that. If double prime at 1, well, x is 1, so it's negative 2/9. And we'll go ahead and do 2 factorial. 2 factorial is just 2. And then f prime at 3, third derivative at, say it right here. Third derivative at 1 would be 10/27. But 10/27 divided by 3 factorial is 6 times x minus 1 cubed. And except for a little cleaning that up, we're pretty much done here. Let's see, negative 2/9 divided by 2 is negative 2/9 times 1/2. So the 2's are going to count, that's negative 1/9. Just do this. That's x minus 1 squared. 10/27 divided by 6. I don't think there's any. Oh yeah, there is. Cancel the 10 and 6. Be 5/3. So it'll be 5/81. X minus 1. That's t cubed x. So it's a little bit of computation, but that's not too bad. You know what I'm talking about there. Definition is of it. Now, here's talking about application. I guess could call this an application. Let's look at the graph of f and t through t3x. And that's where our little calculator come in handy. Cube root of x is not that terribly difficult to graph, but let's see, x raised to the 1/3 is what that looks like. And then it's a little bit cumbersome, I guess, but nothing hard about it, just plug those in. So it'd be 1 plus 1/3 times x minus 1, parentheses x minus 1, minus 1/9 times x minus 1 squared, plus 5/81 times x minus 1 cubed. We graph those two. All right, so the cube root of x, you might want to zoom in a bit. So this is basically negative 2 to positive 2. Comes in like this. Here's cube root of x. And then t cubed x, in this view here, comes in and swoops pretty nicely in along right about here. And it kind of starts veering off, kind of coinciding right about there, but so it, I don't know, you might say, well, it's matching up for a little bit of it. But that was by design here, because why is it kind of matching up right along in here?
That's the first few points.
Huh?
That's the first, it's T3, 1, 2, 3.
Square A.
Yeah.
That's A, yeah. I centered this at A equals 1, right? That's X equals 1. So it makes sense that it would be coinciding or lining up around X equals 1, because that's where I centered that thing. If I wanted it more to match, you know, the curve in here, I would just center it at 0, or wherever I wanted to center that at. So. Okay. All right. Let's try another one here, just to get another look at the other thing.